Welcome to this problem walkthrough. Today, we'll be exploring problem number 2042, check if numbers are ascending in a sentence. In this problem, we'll analyze a sentence, extract numbers, and determine if they appear in strictly ascending order. Let's dive in. In this problem, you are given a string S that represents a sentence. The sentence consists of words and integers, and these are separated by single spaces. Your task is to determine whether the numbers present in the sentence are strictly ascending. That means each number should be greater than the one before it. Now, a word in this sentence is any sequence of characters that doesn't have digits, while an integer is defined as a series of digits without any letters or special symbols in between. Additionally, the numbers will always be positive integers, and they won't have any leading zeros. If there are no numbers in the sentence, the result should be true because there's nothing to compare. The input is a string S, with a length between 1 and 200 characters, and the output is a Boolean value indicating whether the numbers are in strictly ascending order. Let's look at an example. For the input S equals 1 boxes 3 blue 4 red 6 green and 12 yellow marbles, the output is true. This is because the numbers in the sentence are 1, 3, 4, 6, 12, and they are in strictly ascending order. Now consider another input, S equals hello world 5x5. In this case, the output is false because the numbers are 5, 5, and since 5 is not greater than 5, the numbers are not strictly ascending. Here's another example. For the input S equals sun 9 moon 20 stars 21, the output is true. The numbers extracted from the sentence are 9, 20, 21, and since each number is greater than the previous one, they satisfy the condition for being strictly ascending. Now let's revisit some important constraints. The length of the string S will always be between 1 and 200 characters. It will only contain lowercase English letters, spaces, and digits. Words and numbers are always separated by single spaces, and there are no consecutive, leading, or trailing spaces. Lastly, all numbers in the sentence will be positive integers without any leading zeros. Let's consider some edge cases to better understand the problem. First, if the sentence contains no numbers, the output should be true because there's nothing to compare. For example, if S equals this is a test, the result is true. Next, if there's only one number in the sentence, the output should also be true because there's no second number to make a comparison, like in S equals only 42 here. Additionally, the function should handle longer sentences efficiently, as the input length can go up to 200 characters. It should also correctly return false when the numbers are not strictly ascending, such as in S equals 10, 9, 8. Lastly, you don't need to handle numbers with leading zeros, like S equals 0, 1, 10, 20, because the constraints guarantee these won't appear in the input. To tackle this problem, one of the approaches we can consider is the brute force method. The intuition here is fairly straightforward. We process the sentence word by word, extract any numbers, and then verify if these numbers are in strictly ascending order. The process starts by splitting the sentence into individual words using the split function. Then, as we iterate through the words, we check whether each word is a number by using the isdigit function. If it is, we convert it to an integer, store it in a list, and continue this process for all words. Once we have the list of numbers, we compare each number with the one before it to ensure the list is in strictly ascending order. The complexity of this approach is O(n), 4 times, since splitting the string and iterating through the words both require linear time. However, it does have a space complexity of O(k), where k is the count of numbers in the sentence, because we allocate additional memory to store the list of numbers. The main drawback of this approach is precisely this extra space usage, which could be avoided with a more efficient strategy. Now, we can optimize this solution further by eliminating the need to store all numbers in a list. Instead of keeping track of every number, we maintain just one variable, previous, to store the most recently seen number. As we iterate through the words, whenever we encounter a number, we compare it directly with previous. If the current number is not strictly greater than previous, we immediately return false. Otherwise, we update previous to the current number and continue processing. This way, we only keep one piece of state at a time. The steps are simple. First, split the sentence into words using split. Then, initialize previous to a very small number, such as 0. As we iterate, whenever we find a number, we convert it to an integer, compare it with previous, and either update previous or return false based on the result. If we finish processing without any issues, we return true. The complexity analysis shows that the time complexity remains O(n), as we still only traverse the sentence once. However, the space complexity is reduced to O(1), since we no longer store a list of numbers. This makes the optimized approach highly efficient and practical as it reduces both memory usage and implementation complexity. Another alternative we could consider involves the use of regular expressions to extract numbers directly from the sentence. Using a regex pattern, we can identify all numeric sequences in the string and collect them into a list. Once we have this list, the approach becomes similar to the brute force method. We iterate through the numbers and verify if they are in strictly ascending order. While this approach is elegant and compact, there are some notable drawbacks. First, it introduces dependence on regular expressions, which can make the code less readable and harder to debug for those unfamiliar with regex. Additionally, the space complexity is OK, as we still need to store the extracted numbers in a list. In terms of time complexity, extracting numbers with regex is approximately O(n), and verifying the order is OK. Ultimately, we opt for the optimized approach as our chosen solution. It strikes the ideal balance between simplicity, efficiency, and minimal resource usage. By focusing on one number at a time and avoiding unnecessary storage, the optimized approach avoids the space overhead of the brute force method and the added complexity of regex-based solutions. This makes it the most practical and performant choice for solving the problem effectively. To solve this problem, we start by breaking down the algorithm into clear steps. First, we need to parse the input sentence. For example, if the input is the temperatures are 20, 25, and 30 degrees, we use the split function to divide the sentence into individual words. This will give us a list of strings such as the temperatures are 20, 25, and 30 degrees. Next, we initialize a variable called previous_number and set it to none. This will help us keep track of the last numerical value we encountered in the sentence. Then, we iterate over the list of words using a for loop. For each word, we use the isdigit method to check if it represents a numeric value. This ensures that non-numeric words like degrees or and are ignored, while numeric strings like 20 or 25 are processed. This setup allows us to focus only on the numbers within the sentence while systematically ignoring everything else. Once we identify a numeric word, the next step is to extract and compare it with the previous number. If the current word passes the isdigit check, we convert it into an integer using int. Now we compare this integer with the previous _number. If previous _number is still set to none, it means this is the first number we've encountered, so we simply update previous _number to the current number. Otherwise, we compare the current number with previous _number to ensure it is greater. If it is not greater, we return false immediately since the sequence is no longer strictly ascending. If the condition is satisfied, we update previous _number to the current number and continue to the next word. Finally, if we complete the loop without finding any violations, it means all numbers in the sentence are in ascending order, and we return true. Breaking down some key insights from this algorithm, we can see why each part of the process is necessary. Splitting the sentence into words is crucial because it allows us to isolate and process each word individually. The isdigit check is another critical step. It prevents errors by ensuring that only valid numeric strings are converted to integers. Using a single variable, previous _number, to store the last number encountered keeps the algorithm efficient and easy to follow. This approach minimizes memory usage while ensuring accurate comparisons. Additionally, the early exit optimization, returning false as soon as a pair of numbers violates the ascending condition, saves time by avoiding unnecessary processing of the remaining words. In terms of data structures, the algorithm relies on a list of words for sequential processing and a single integer variable for comparison, which keeps the implementation lightweight. The algorithm's efficiency can be analyzed in terms of time and space complexity. For time complexity, splitting the sentence into words takes O(n), where n is the length of the sentence. Iterating through the list of words is also O(n), so the overall time complexity is O(n). For space complexity, the list of words requires O, W, space, where W is the number of words in the sentence. The previous underscore number variable uses constant space, O1. Therefore, the overall space complexity is O, W. Now, let's consider some edge cases. If the sentence contains no numbers, like hello world, the result is true since there are no numbers to violate the condition. If there's only one number, as in temperature is 42, the result is also true because there's no second number to compare. Words like 20 or degrees are ignored since they don't pass the isdigit check. Additionally, negative numbers or decimals would require extra handling, as they are not supported by the current algorithm. Let's walk through an example to see how the algorithm works. Consider the input sentence, the temperatures are 20, 25, and 30 degrees. First, we split this into words, resulting in the list, the temperatures are 20, 25, and 30 degrees. We initialize previous underscore number as none and start iterating through the words. The first three words, the temperatures, and are not digits, so we skip them. When we reach 20, it passes the isdigit check, so we convert it to 20. Since previous underscore number is none, we set previous underscore number to 20. Next, we process 25 foot, which is also a digit. We compare it with previous underscore number, which is 20, and since 25 is greater, we update previous underscore number to 25. We skip the word and because it's not a digit. Then we process 30, convert it to an integer, and compare it with previous underscore number, which is now 25. Since 30 is greater, we update previous underscore number to 30. Finally, the word degrees is skipped. All numbers are in ascending order, so the algorithm returns true. This Python implementation solves LeetCode problem number 2042, check if numbers are ascending in a sentence. The problem requires us to determine if the numbers present in a given sentence appear in strictly ascending order. The solution begins by splitting the input sentence into individual words using the split function. This produces a list of words, which includes both numeric and non-numeric tokens. Next, a variable prev underscore number is initialized to -1, representing a value smaller than any valid number in the sentence. The algorithm then iterates through each word in the sentence. For each word, it checks whether the word represents a number using the isdigit method. If the word is numeric, it is converted to an integer, and the algorithm compares it with the last encountered number, stored in prev underscore number. If the current number is less than or equal to prev underscore number, the function immediately returns false, as the numbers are no longer in ascending order. If the current number is valid and greater than the previous number, the prev underscore number variable is updated to the current number, ensuring that subsequent comparisons use the latest value. At the end of the loop, if all numbers in the sentence have been processed without violating the ascending order condition, the function returns true. This ensures that the solution handles all edge cases, including sentences without numbers and sentences with numbers interspersed with text. The solution is efficient, as it processes each word in the sentence exactly once, resulting in a time complexity of O(n), where n is the number of words in the sentence. The space complexity is O(1), as no additional data structures are used beyond a few variables. Together, these properties make the solution both elegant and performant for the given problem. Here, we start by splitting the input sentence into individual words using the split method. This breaks down the sentence into an array of strings, making it easier to process each word one by one. Next, we initialize a variable prev number to -1. This acts as a placeholder for the last number we encountered, starting with a value that's smaller than any valid number in the sentence. Then, we iterate through each word in the array using a for loop. For every word, we check whether it represents a numeric value using a helper method called isNumeric. If the word is numeric, we parse it into an integer and store it in a variable current number. At this point, we compare current number with prev number to ensure that the numbers are in strictly ascending order. If we find that current number is less than or equal to prev number, we immediately return false, as the condition for ascending order is violated. Otherwise, we update prev number to the current number and continue checking the remaining words. Finally, if all numbers pass the check, we return true to indicate that the numbers are ascending. The helper method isNumeric is defined to determine whether a given string represents a valid number. This method uses a try-catch block to safely attempt parsing the string into an integer. If the parsing succeeds, the method returns true, indicating that the string is numeric. However, if a number format exception is thrown, the method catches the exception and returns false, indicating that the string is not a valid number. This approach ensures that we can reliably differentiate between numeric words and non-numeric words in the input sentence without causing runtime errors. By combining this helper method with the main logic, we create a robust solution to verify whether the numbers in the sentence are in ascending order. Here, we have a simple example to understand how the solution works. The input sentence is 1 box is 3 blue 4 red 6 green and 7 yellow marbles. First, we split the sentence into individual words, which gives us a list of words including both numbers and non-numeric words. We initialize prev_number to -1 to keep track of the last valid number we processed. Then, we iterate through each word in the list. For the first word, 1, we check if it is a number using the isDigit method, which returns true. We convert it to an integer, compare it with prev_number, and since 1 is greater than -1, we update prev_number to 1. Next, we encounter non-numeric words like box and has, and we simply skip over them. When we reach the word 3, we identify it as a number, convert it to an integer, and compare it with the previous number, which is now 1. Since 3 is greater than 1, we update prev_number to 3 and continue this process for the remaining numbers, 4, 6, and 7. Each time, the numbers are greater than the previous one, so we keep updating prev_number. By the end, all numbers are in ascending order, so we return true as the output. In this example, the input sentence is 1 box has 3 blue 2 red marbles. Again, we split the sentence into words and initialize prev_number to -1. As we iterate through the words, we first encounter 1, which is a number. We convert it to an integer, compare it with prev_number, and since 1 is greater than -1, we update prev_number to 1. Next, we find 3, which is also a number. Converting it to an integer, we compare it with the last number, 1, and since 3 is greater than 1, we update prev_number to 3. However, when we reach 2, we again identify it as a number and convert it to an integer. This time, when we compare 2 with the current prev_number, which is 3, we find that 2 is not greater than 3. Since the condition for ascending order is violated, we immediately return false without continuing further. The output for this example is therefore false. Now, let's look at a case where the input sentence, "Hello world, this is a test sentence," contains no numbers at all. After splitting the sentence into words, we initialize prev_number to -1, just as before. As we iterate through the words, we check each one to see if it is a number using the isDigit method. In this case, none of the words, such as hello, world, or test, are numbers. Since there are no numbers in this sentence, there's nothing to compare. By definition, the absence of numbers means the condition of ascending order is trivially satisfied. Therefore, we return true as the output for this example. To analyze the time complexity of this algorithm, we start by looking at the key operations involved. First, splitting the input string into words using s.split, scans the entire string and divides it into parts based on spaces. This operation processes each character exactly once, resulting in a time complexity of O(n), where n is the length of the string. Next, we iterate through the list of words using a loop. If there are k words in total, the combined length of all these words still adds up to n. This means that the iteration step also takes O(n) time cumulatively. Within the loop, we check if each word consists of digits using the word.isDigit method. Since this check involves inspecting each character within a word, the total time required for this operation across all words is also proportional to the total string length n. Each of these steps contributes to the overall time complexity in a linear fashion. Next, let's examine the integer conversion step, where numeric words are converted into integers using int word. This operation depends on the length of the word being converted, but since the total length of all numeric words is at most n, the time spent on this step is cumulatively O(n). Combining all these operations, the algorithm processes each character in the string a constant number of times, resulting in an overall time complexity of O(n). Now turning to space complexity, the algorithm requires memory to store the list of words generated by s.split. The total space used for this list corresponds to the combined length of the words, which is O(n). Additionally, there is a single integer variable prev_number used to store the most recent number, which takes constant space, or O(1). Looking deeper into the space requirements, the integer conversion step itself does not need extra memory beyond the space already allocated for the word being processed. The converted integer is simply stored in the same variable. Thus, there are no additional data structures beyond the words list, meaning the overall space complexity remains O(n). Comparing this approach to a brute force method, a naive solution might involve manually parsing the string character by character to identify spaces in numbers. While this would also have a time complexity of O(n), it would involve unnecessary overhead and make the implementation more cumbersome. The current solution, on the other hand, is both time efficient and memory efficient, as it processes the string in a streamlined, logical manner without extra computations. Finally, let's consider the best, average, and worst case scenarios for the algorithm. In the best case, if the sentence contains no numbers at all, the algorithm still processes each word in the string, resulting in O(n) time complexity. In the average case, where some words are numbers and others are not, the algorithm still needs to iterate through the entire string, so the time complexity remains O(n). Even in the worst case, where every word in the sentence is a number, the time required to process each character remains proportional to the length of the string, so the time complexity is still O(n). The space complexity also stays consistent at O(n) due to the list of words. In summary, the algorithm exhibits O(n) time and O(n) space complexity across all scenarios, making it highly efficient and well suited for this problem. When solving this problem, there are a few common mistakes to watch out for. One frequent oversight is failing to handle edge cases properly. For example, if the sentence doesn't contain any numbers, or only has one number, it's easy to miss these scenarios during implementation. To avoid this, make sure to explicitly check for empty inputs, single numbers, or sentences without numbers at all. Another mistake is incorrectly handling non-numeric words. If the code assumes every word is a number, it could fail when encountering something like apple or other non-numeric text. To address this, use robust type checking or filtering mechanisms to ensure only valid numbers are processed. Finally, skipping input normalization can cause issues. For instance, numbers attached to symbols like 45 might not be parsed correctly. Pre-processing the input by normalizing punctuation and converting everything to lowercase can help ensure consistent behavior. Now, another area where mistakes often occur is in the use of strict comparisons. Using non-strict operators like greater than or equal to instead of greater than can lead to incorrect results, especially if numbers are repeated in the sentence. To fix this, ensure your condition explicitly checks for a strictly increasing order. Additionally, inefficient parsing can be a problem, such as iterating over the sentence multiple times to first extract numbers and then check conditions separately. This approach can become inefficient, particularly with larger inputs. To optimize, consider combining the parsing and checking steps into a single pass to streamline the process. In an interview setting, there are a few key insights to remember. First, focus on recognizing patterns in the problem description. Phrases like strictly increasing or numbers in a sentence often suggest specific operations such as parsing or comparison, so train yourself to pick up on these cues. It's also important to think about edge cases early. Discussing scenarios like empty inputs or special characters with the interviewer shows that you're thorough and detail-oriented. Another tip is to optimize incrementally. Start with a simple, brute force solution to make your approach clear, and then refine it for efficiency while explaining your thought process. Finally, take advantage of built-in functions where appropriate. For instance, Python's isdigit or list comprehensions can simplify parsing, but be prepared to implement solutions manually if the interviewer asks you to. Related problems, such as LeetCode 58 or 151, can help you practice similar concepts, so exploring these can be a great way to prepare. There are also alternative approaches you can consider for this problem. One option is the two-pointer approach, which allows you to compare numbers as you parse the sentence instead of storing them all first. This method can save memory, but it might be less intuitive to implement. Another approach involves using regular expressions to extract all numbers from the sentence in one step, followed by checking for a strictly increasing order. While this method is concise, it might be overkill for simpler inputs. Finally, a functional programming approach using tools like map and filter can streamline the extraction and processing of numbers. However, this might come at the cost of readability, especially in an interview setting. Each of these methods has its trade-offs, so choose the one that best fits the context of the problem and the constraints you're working with. Great job! To recap, we solved the problem by efficiently parsing a sentence and checking if the numbers were in ascending order. Remember to practice string manipulation and comparison logic for similar problems. Thanks for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!